Today we shall study about diffraction in wave optics. Now, if we look clearly at the shadow caused by an opaque object close to the region of geometrical shadow, there are alternate dark and bright fringes just like in interference. This happens due to the phenomenon of diffraction. Diffraction is a general characteristic exhibited by all types of waves, but be it sound waves, light waves, water waves, or matter waves. Since the wavelength of light is much smaller than the dimension of most obstacles, we do not encounter diffraction effects of light in everyday observations. However, the finite resolution of our eye or of optical instruments such as telescopes or microscopes is limited due to the phenomenon of diffraction. Indeed, the colors that you see when a CD is viewed due to diffraction effects. We will now discuss the phenomenon of diffraction. Single slit. In the discussion of Young's experiment, we stated that a single narrow slit acts as a new source from which light spreads out. Even before Young, early experiments, including Newton, had noticed that light spreads out from a narrow holes and slits. It seems to turn round corners and enter regions where we would expect a shadow. These effects, known as diffraction, can only be properly understood using wave ideas. After all, you are hardly surprised to hear sound waves from someone talking around a corner. When the double slit in Young's experiment is replaced by a single narrow slit illuminated by a monochromatic source, a broad pattern with a central bright region is seen. On both sides there are alternate dark and bright regions. The intensity became weaker away from the center. To understand this, go to the figure 1, which shows a parallel beam of light falling normally on a single slit ln of width A. The diffracted light goes on to meet a screen. The midpoint of slit is M. A straight line through M perpendicular to the slit plane meets the screen at C. We want the infinity at any point P on the screen. As before, a straight line of rising P to the different points L, M, N, etc. can be treated as parallel, making an angle A with MC, theta with MC. The basic idea is to divide the slit into much smaller parts and add their contributions at P. With the proper phase differences, we are treating different parts of the wavefront at the slit as secondary sources. Because the secondary wavefront is parallel to the plane of the slit, these sources are in phase. Now, the part difference LP minus NP NP LP minus NP minus NP between the two edges of the slit can be calculated exactly as for the Young's experiment. From figure 1, NP minus LP बराबर n theta बराबर a sin theta बराबर a theta for a smaller angle. Similarly, if the 2 points M1 and M2 in the slit plane are separated by the path difference M2P minus M1P barabar by theta, we now have to sum up equal coherent contributions from a large number of sources, each with a different phase. The calculation was made by Fresnel's using integral calculus, so we omit it here. The main features of the diffraction pattern can be understood by sample arguments. If the central point C on the screen, the angle theta is 0, all path differences are 0, and hence all the parts of the result contribute in phase. This gives maximum intensity at C. Figure 1 indicates that the intensity has a central maximum at theta barabar 0 and other secondary maxima at theta barabar n plus 1 by 2 into lambda by a, and has maximum 0 intensity at theta barabar n lambda by a. Consider first the angle theta where the part difference is a theta is a part difference is lambda, so theta barabar lambda by a. We now compare and contrast the interference pattern with that seen for a coherently illuminated single slit. The interference pattern has a number of equally spaced bright and dark bands. The diffraction pattern has a central bright maximum, which is twice as wide as the other maxima. The intensity falls as we go to successive maxima away from the center on either side. Second, we calculate the interference pattern by superposing two waves originating from the two narrow slits. The diffraction pattern is a superposition of a continuous family of waves originating from each point on a single slit. For a single slit of width A, the first null of the interference pattern across at an angle of lambda by A at the same angle of lambda by A, we get a maximum for the two narrow slits separated by a distance A. One must understand that both A, D and A have to quite small to be able to observe good interference and diffraction pattern. In interference and diffraction, light energy is redistributed. If it reduces in one region producing a dark region, it increases in another region. producing a bright fringe. There is no gain or loss of energy which is consistent with the principle of conservation of energy. Now the resolving power of optical instruments, as shown in the figure 1, the angular resolution of the telescope is determined by the objective of the telescope. The stars which are not resolved in the image produced by the objective cannot be resolved by any other magnification produced by the eyepiece. Consider a parallel beam of light falling on a convex. If the lens is well corrected for aberrations, then geometrical optics tells us that the beam will get focused to a point. However, because of diffraction, the beam, instead of getting focused to a point, gets focused to a spot of finite area. In this case, the effects due to diffraction can be taken into account by considering a plane wave incident on a circular aperture followed by a convex lens. The analysis of the corresponding diffraction pattern is quite involved. However, in principle, it is similar to the analysis carried out to obtain the single slit diffraction pattern, taking into account the effects due to diffraction. The pattern on the focal plane would consist of a central bright region surrounded by a concentric dark and bright rings. A detailed analysis shows that the radius of the central bright region is approximately given by RO बराबर 1.22 lambda f by 2a बराबर 0.61 lambda f by a, where f बराबर focal length, 2a बराबर diameter of the circular aperture. Typically, if lambda बराबर 0.5 μm, f बराबर 20 cm and a बराबर 5 cm, we have RO बराबर 1.2 μm. Although the size of the spot is very small, it plays an important role in determining the limit of resolution of the optical instrument. Like telescope or a microscope, for the two stars to be just resolved, f delta theta बराबर RO बराबर 0.61 lambda f by a, implying delta theta बराबर 0.61 lambda by a. Thus, delta theta will be small if the diameter of the objective is large. This implies that the telescope will have better resolving power if A is large.